Hello there, Past Paper Guy here today. I am going to be solving the assessment materials from 2021 AQA. So these are the ones released. I'm going to release this video as soon as they go public. And this is the second set, which is the particles, radiation, and nuclear physics. Like the previous video, I'm not going to be projecting the actual questions because of AQA's quite strict copyright policy. So you'll need to download the paper, print off a copy so you can follow along. Question 1 then is taken from the June 2019 paper and is a relatively straightforward question about isotopes. So 1.1 is asking for a difference between the constituents of these two nuclei. Remember, whenever something asks for a difference, always mention both. So the iodine 131 has, and then be explicit about the difference. So it's not just more neutrons, but 6 more neutrons than iodine 125. Question 1.2, dead easy. What do you know what a nucleon number is? 131. Question 1.3. So we've got 12553 iodine, and we're going to capture an electron which has a charge of -1 like that. So we're going to end up with 12552 something plus an electron neutrino. Now we need to look at the differences between this and this. This is tellurium. So it has the same nucleon number, but it's got tellurium has 1 fewer proton and therefore it has 1 more neutron. So again, always mention both when you do the that's a U, when you do a difference. So tellurium has 1 fewer proton, tellurium has 1 more neutron, and then we want to put than iodine. 125. So that was question 1. Question 6 now. This one is from the June 2020 paper. A thermal nuclear reactor uses enriched uranium. It's got uranium-235 and uranium-238. And it's asking what happens when it interacts with neutrons in a thermal nuclear reactor. Okay, so let's do each one separately. So thermal neutrons means that they're moving relatively slowly. So it's a thermal nuclear reactor. So there must be a moderator in there slowing down the neutrons. So we can say that thermal neutrons, so those are reasonably slow ones, they can collide with uranium-235, and when they do, they get absorbed, or they can be. And that makes uranium-236. Uranium-236 is fissile. So uranium-235 is what's called fertile. It can be turned into a fissile material. So uranium-236 is fissile and will break into several daughter nuclei and release 2 or 3, and these neutrons will be fast moving. Okay, so that's enough about uranium-235. I think we're looking for a total of 3 marks. So let's talk about uranium-238 for a bit. Also, uranium-238 can also absorb thermal neutrons. To make uranium-239. Now, uranium-239 is not fissile, so don't say that it is, otherwise you'll be marked down. But it does undergo beta decay twice, I think. So we'll just put beta decays in there to become plutonium-239, which can also be used as a fuel. So that would be in a different reactor usually. That's loads of detail there that will easily get us all 3 marks for that one. Question 6.2. This is a reasonably straightforward use of a decay equation. So the decay equation is of the form m is equal to the original mass e to the minus lambda t. You can put in place of m, you can put n, the number of molecules, or n, the number of moles, or you can put the activity. They're all directly proportional to each other. So you can shove the numbers in now, or we can rearrange it. We want to find the original mass. So we've got m naught is equal to the current mass divided by e to the minus lambda t. Okay, well, we can do that. So lambda and t we can leave in years because they're both put in years. So we've got 1.54 times 10 to the minus 10. Let's write this out. 993 grams divided by e to the minus 1.54 times 10 to the minus 10 times by the age of the rock, and because they're both in years they'll cancel each other. That one's in 1 over years, that one's in years, they'll cancel each other out. So you don't need to worry about the time as long as they match. So we've got that there, so we want to do e to the power minus answer, and we get that, and we do 993 divided by answer is equal to 1351 grams, which is approximately 1.4 kilograms to SF. There we go. Six dot 3. Okay, so this is working out the percentage of the material. So we need to try, the sample contained 52 grams of uranium-235 2 billion years ago, and in the previous question we've just worked out that the new amount of uranium-238 at that time was 1,351 grams. We want to find this as a percentage of the total uranium, so we add in the 52 grams for that as well. So add in 52 and then do 52 divided by the answer times by 100 to turn it into a percentage. Gives us 3.7%. So the uranium-235, that's the uranium-235 there, that's the uranium-238 and the uranium-235. So it's uranium-235 as a percentage of the total. It's 3.7, so it would be high enough? I like this question because it says, deduce whether the sample had a high enough uranium-235 content to be used in a reactor 2 billion years ago. Well, the answer is obviously no, because there were no reactors 2 billion years ago. Silly question. Question 6. This question 6 is from June 2018. Now, to start with, you're given a decay graph like so. Now, you're asked to be what would the value of the quantity which is decaying, which starts off at 16 here, what would the value of the quantity which is decaying be after 57 seconds? Okay, so this is actually much easier than you might think initially. If you look at the graph, there's a really nice point. If you look at 8 there and go along and down, you'll find that is at exactly 19 seconds. So that means that 19 seconds is equal to the half-life. So if we start at 16, it will go to 8 after 19 seconds. It will go to 4 after another 19 seconds, and it will go to 2 after a third 19 seconds, which is 57 seconds. So this one is 6.2, and we're suggesting how the apparatus could be modified to represent the same radioactive thing, but with a greater number of nuclei. Okay, so that means that you need to have a greater number of nuclei, you just need more water in the cylinder. So more water, so a higher depth in the cylinder. And it's the cylindrical tube rather than... It's always a good idea to use the terms that are from the tape and from the diagram. So that would represent more of the isotope, so it would take a while just to get to the level that you had before, which is representing it decaying down to the amount that you had to start with, and then suggest how the apparatus could be changed to represent a radioactive sample nuclide with a smaller decay constant. Well, for this one, we need to make it so that the water flows out less quickly. So the easiest way to do that I thought was use a thinner, narrow tube. But there are other ways. You could, for instance, tighten the tap a little bit as well. That would also work. Well, A is equal to A naught e to the minus lambda t. So A over A naught, take a log of that, is equal to minus lambda t. If this is a half, then we've got ln of a half is equal to minus lambda t a half. And so that's log of minus log of 2, that cancels with that there. So we get ln of 2 over lambda is equal to t a half. Now I can't remember if that's actually on the formula sheet. It might be written on the formula sheet like that. So we just need to shove the numbers in. So we have ln of 2, and then we divide that by the radioactive constant, which is 1.40 times 10 to the minus 11, and this will give us an answer in years. So t a half will be equal to 4.88 years times 10 to the 10 years. Quite a bit more than 4.88 years. This question has a couple of things you need to take care on. The units they want it in grams, so if you worked it out in milligrams, you need to change it at the bottom, and it's a significant figured one. So we start with the new mass is equal to the old mass e to the minus lambda t. So the old mass is going to equal the new mass divided by, the new mass divided by e to the minus lambda t, which is equal to 1.23, so I'll do it all in milligrams to start with, divided by e to the minus 1.42 times 10 to the minus 11 times by, and the time it's been decaying for is 4.47 billion years. And again, they're both in years, so you don't have to worry about it. So I'm going to work out this bottom bit first. Minus, put them in brackets, minus 1.42 times 10 to the minus 11 times by 4.447 times 10 to the 9. And we get that, and then we need to do 1.23 divided by that, and we get 1.31 milligrams. So our final answer is 1.31 times 10 to the minus 3, because we're changing milligrams into grams, and then that's to 3 significant figures. And it's all to 3 significant figures because all the data in the question is 3 significant figures. In this question, we're going to use the result that the activity is equal to n lambda. Now the units that we're going to want at the end are seconds to the minus 1, which is the same as a becquerel, counts per second. In the mark scheme, they don't give any provision for doing it in counts per year, so make sure that your unit changes it to counts per second. So we've got to be careful because the activity, the decay constant here is given in per years. So first of all, we need to turn 1.23 milligrams into a number of particles. So the way I usually do this is I change it into grams. There are multiple ways you can do this. Divide by its relative atomic mass, 87. That's going to give you an approximate number of moles. And then we're going to times by Avogadro's number, because n is equal to the mass in grams divided by the relative atomic mass times by Avogadro's number, because that's the number of moles there. So let's work out what that is before we do anything else. So we've got 1.23, it's milligrams, so times 10 to the minus 3, divided by 87, so that's the number of moles. Then we times by Avogadro's number, which is 6.022 times 10 to the 23, and we get the number of atoms in our sample is 8.5138 times 10 to the 18. Okay, then we can use this equation here. So the activity is equal to n lambda. So let's just multiply those two numbers together. 5138 times 10 to the 18 times by lambda, which is 1.42 times 10 to the minus 11. So times those together. And that is the activity in a year. So activity is 120 it's 121 times 10 to the 6, isn't it? And that's per year. So we now need to think, well, in a second, it's going to be less than that, isn't it? So we divide by the number of days, divide by the number of hours, divide by the number of seconds in an hour, and we get 3.8. So the activity is equal to 3.83 counts per second. So our final answer is 3.83 counts every second. Okay, there's lots of converting units in that particular one, which I guess is why it's 3 marks. And 2, and this is from the paper June 2018. The first part is relatively easy. Show that the data is consistent with the relationship lambda is proportional to 1 over v. That means that lambda v should be equal to some constant. So I just added a new column of the table, lambda v, which has the units of times 10 to the minus 4 meters squared over seconds. And you multiply those values together and you get 7.35, 7.25 and 7.35. And then just a short statement to the effect that lambda v is almost constant, so consistent with lambda is proportional to 1 over v. Not too tricky. Then we need to calculate a de Broglie wavelength. We need to calculate Planck's constant from that de Broglie wavelength. So we know that lambda is equal to h over the momentum. So we got h is equal, Planck's constant h is equal to lambda v times by m. So we know what that is already. We can look that up. So we've got lambda v, I just used 7.35. You could take an average of those if you wanted. Make sure that you get your powers of 10 right, because you've got, in the table, you've got a times 10 to the 7 and a times 10 to the minus 11. So make sure you get your powers of 10 right. And then times by 9.11 times 10 to the minus 31, which is the mass of an electron. And you get 7.35 times 10 to the minus 4 times by 9.11 times 10 to the minus 31, and that gives you 6.6958 so that's 6 times 10 to the minus 34, so that's 6.7 times 10 to the minus 34 to two significant figures. 6.7, which is acceptable. If you used a different value for here, if you use the average, you might get a slightly different answer there. Question 2.3 is about electron diffraction, and the first part of it is to explain how the pattern produced. So we've got this circular pattern here. We've got a spot in the middle, a bit blurry around the outside of that spot. My one's obviously the opposite in colours to the one that they've printed. So these distinct rings and then the spot in the middle. So what's happening is the spot in the middle is caused by electrons just going straight through. This blur around the outside of the spot in the middle is scattering. That's particle-like behaviour. And then these distinct rings are caused by interference, which is definitely wave-like behaviour. So we are asked to talk about how it's behaving like a wave. So we need to talk about these rings here. And we need to draw a comparison between that and how it would act if it was like a particle, which is that we would see a blob in the middle with it getting lesser and less around the outside as the scattered electrons, most of them go straight through, but some of the scattering's a little small angle and less scattering is at a bigger angle. So let's talk about that. So the rings are seen because the electrons behave as a wave and diffract, that's your key word there, as they pass through. And the material they're passing through is carbon, is it? Yeah, graphite. As they pass through the graphite. Right, that's not enough though. We've said that they diffract, but we haven't said why they form the rings. So in the bright areas, the path differences are a whole number of wavelengths, that means that the waves, when they arrive in phase, so the waves are in phase and constructively interfere. There we go. So we've talked about interference, we've talked about the diffraction. So the diffraction leads to the path difference, which leads to the interference. Let's talk about the darker regions, this one here. So the dim regions are caused by, well, there the electrons are still diffracting, but when they meet their outer phase, by the path difference of the diffracted electrons not being n lambda, some whole number of lambda, so they are out of phase and they destructively interfere. Now for this question it says behaving as a wave rather than a stream of particles. So I think it's important to say if it were a stream of particles. If it were a stream of particles, you would only see, now put only in there, I'm not going to fuss about that, but because you do see this, you do see a bright dot in the middle and then a blur around the outside where it's scattered. You'd only see a bright spot in the middle where most electrons go through, and a blur around where some are scattered, and it's a reducing amount. So I think we need to put that comparison in there. Now it looks like a lot, but there's a lot to say. It's an important experiment, and I think that completely answers the question to anybody's satisfaction. Explain how the emissions of light from the fluorescent screen show that the electrons incident on it are behaving as particles. And this is 3 marks, so we're going to need to put quite a bit of detail in this to get all 3. So we need to link all the way to light being emitted. So what's going to happen is in your fluorescent material, you're going to have the electron coming in, and it's going to hit an electron here, and it's going to bounce off, and it's going to smack this electron into either a higher energy or it's going to ionize it. And then when this falls back down again, that's going to emit light, which is how the light comes about. So I think we just need to describe that procedure really. So each incoming electron can collide with one orbital, and that's important. Whenever you're talking about particles, remember that the electrons hit a single orbital electron in the same way that in photoelectricity, which this is not a question about, the photons interact with one electron. Always worth mentioning, it's a one-to-one. If you're thinking of them as particles, they have to hit one-to-one rather than many-to-many. So each incoming electron can collide with one orbital electron and excite it to a higher energy level or ionize it. And it does that by transferring kinetic energy from the colliding electron to the orbiting electron. Okay, so that is the particle behaviour. Now you might just leave it at that because you've explained why. So this is particle behaviour. You might think you leave it at that because you've explained about the particle behaviour, but it says about the emission of light. So we need to then describe how that leads to emission of light. So as the orbiting electron, so this isn't particle behaviour now, but as the orbiting electron falls down energy levels, it releases photons which is the light we can see. Right, so again it's 3 marks, so you expect quite a lot of detail there. 6.4, this was taken from the June 2019 paper, and it's a mass defect question. So all you do is you add up all the mass on the left hand side. So we have 1 uranium, which is 235.044, and we added 1 neutron, which is 1.0087. If you're clever, you could cancel a neutron each side, but I'm just going to do it the brute force method. So that gives you 2, and that's all in U's. So that gives you 236.0527 U. And then the right hand side is going to equal 1 xenon U thing, so that's 141.92, reading 930, plus 1 strontium, which is 89.908, plus 4 neutrons, so that's 4 times by 1.0087, and that's all in U as well. Make sure you keep all of your decimal places. I'm just going to store that so I can get it back. Okay, so that's 235.8728. Remember to keep all of your decimal places, because the difference between them will be tiny. So we take away A, and we get the mass defect. So delta M is the difference between those two. Is going to equal 0.1799 U's. Now you could convert that into kilograms, convert that into joules using E equals mc squared, and convert that into mega electron volts. But it's much easier to just convert it straight into an energy. And to do that, you'll find on the formula sheet, which I'm not going to show you, there's a number which is 931 point, I don't know how many decimal places they give it to, which this is the energy of a single U. It's written on your data sheet. So you don't have to go through all of those intermediate steps. You just times by 931, and that is in mega electron volts already. So we just times it by 931.4936. I might have more decimal places than you do there. 167.5756 MeV. So that converts it straight into mega electron volts, which is 167 MeV 3SF. We're on to the multi-choice now. Question 29 is from the 2020 paper, and you have various quantities about a decay, and you need to remember that the activity is equal to n lambda, so therefore the activity is directly proportional to n, which is answer A. Question 9 now, which is from June 2020, and we have this here, so you just add up the numbers on the top. And you add up the numbers on the bottom. So this one has to be a 1, this one has to be a 0, and that is of course a neutron with no charge, 1 mass. So that is answer B. Next one, question 10 from the same paper. You've got 232 thorium, and it's 90 there. So it's 1 alpha and 2 betas. So the alpha will make it a 22888. Then that's an alpha. A beta will make it, will not change the top number, but increase this. And then another beta will be not change the top number, but increase that. So that must be one of the options. Let's see, option C. Question 9. This one is from June 2019. An electron collides with an isolated atom and raises an orbiting electron to a higher energy level. Which statement is correct? Well, the only one that makes sense there is D, the energy transferred to the colliding electron to the orbiting electron. The others are nonsense. Question 13 is from the June 2020 paper. Which graph shows a variation of the momentum P with lambda of a photon? So lambda equals h over p, so p is equal to h over lambda, which means that p is proportional to 1 over lambda, which we had in the previous question. So that means you're looking for a 1 over r graph. So it's a graph that looks like that. It does not touch there, nor does it touch down there. So it's got to be A rather than B, because B is more like a decay curve where it touches here. Question 30, which is taken from June 2020. We've got a mass defect question. So we just take the lithium, which is 7.01436. We take away its constituents, which is 3 protons, and 4 neutrons. And we do that, so we have 7.01436, take away 3 times by a proton, 1.00728, and we need to take away 4 neutrons worth, so times by 1.00867, which gives us the mass defect of 0.04216 U's, which is answer B. Question 31. Right. So there's quite a few steps on this one. So we have 0.23 U of energy of mass is lost in a single event. So 0.23. So we need to times by the magic 931 to turn it into mega electron volts. So that's how many mega electron volts are released per event. It's 25% efficient, so we divide it by 4. That gives us how much mega electron volts are released, are transformed into useful power, useful energy each event. We need to remember that's mega, so times it by 10 to the 6. Okay, now we need to change that into joules. So we times by 1.6 times 10 to the minus 19 to change electron volts into joules. And then we want 900 megawatts. So that's 900 megajoules of energy each second. So do 900 divided by that answer gives us 1.05 times 10 to the 20, which is, lo and behold, C. Okay, lots of steps in that one. And that is the end of the second assessment. So I hope you find this video useful. Please do share it with your colleagues, and I wish you all the very best in getting grades and getting to university or wherever it is that you want to go this year, because it's been a really tough year for you guys. So good luck.